Hi, this is a video demonstrating the transmission of an image over an air gap using OFDM.
As part of this, we are required to convolutionally encode our data into an audio file in preparation for the transmission.
We are going to be using these speakers and this microphone and this amazing cardboard box to transmit the audio through.
The box is so that there will be inter-symbol interference created, and the jacket in here is to slightly reduce these reflections. It is also to make sure that there is no direct line of sight between the speaker and the microphone. This is us preparing our data for transmission. We're about to take an image, this image here, and we're going to encode it into a WAV file for transmission.
Using this transmit OFDM MATLAB file. Should actually run it.
Okay, run. It'll take a couple of minutes to run. There we go. Let's test the WAV file that we've produced.
And with no speakers plugged in, so this
Speakers haven't been plugged in, so we will just cut to the actual sending of data. This is our transmission side, and this is our receiver side. We're using socks on both sides, on both transmission and receiving sides. So in the box, you can see we've got a microphone on our receiver side, speaker on the transmission side. Okay, so let's get to it.
Ready?
On 3, 2, 1. So that was the end transmission, and now we're going to go ahead and try and decode the received audio file.
Alright, so we've got 3 different M files for 3 slightly different methods of decoding our received signal. The first one we've got is it's called receive OFDM no phase. It's not using the phase of the pilots to correct the start of the signal, it's just using the cyclic prefix. It detects the peak of the cyclic prefix and then says, alright, okay, this is basically the start of the symbol. And then it reads the whole peak, it says, okay, that finds the max, says this is the symbol start, and then goes through the rest of the decoder. So it's basically, you know, doing the bandpass demodulation right there, and then it's remapping the Fourier spectrum in that bit, getting all the frequencies in the right order, and then skipping the pilots, getting rid of the pilot tones, convolutionally decoding the data, just in the same way we convolutionally encoded it. It's, you know, the receiving side is convolutionally decoding it, and the bit stream, and then XORs with the pseudo-random data, and that should give us, well, should, you know, as an attempt at getting our image back. So just give that a run. Alright, so that's gone through and tried to decode, to not a huge amount of success. You can still kind of make out his face, but it's inverted. It's not exactly been a good decoder, basically. And that's yeah, it's not great. So there's all our peaks from our cycle prefix, and we can see it's taken like 32 seconds in total to run.
So let's move on to the next method.
Percent error rate is 89% for
Not
no
very good.
phase.
Therefore, only 11% retrieved. Obviously.
So now we're going to go on to our second M file, our receive M file, which uses the phase angle of pilots at the current position, and then uses that to adjust the phase of the complex frequency signals. And we're doing that with this line here in particular. Again, we're still using the cyclic prefix for coarse tuning up the top. If we run this file, this takes roughly the same amount of time as no phase. However, it has a much better bit error rate, or much less bit error rate. We should see around 14 or 15% error. We can already see it's much improved. There we are, it's recognisable.
Taken almost the same time.
Just slightly longer, but vastly improved image recovery.
Okay, and from there we've got our final method. What we do here is it's slightly more computationally expensive. So our code is exactly the same. We're still finding our each one of our cyclic prefix starts here. This is becoming our symbol start. So we run through for each of these symbols, and what we're doing here is on this line, we're taking our coarse detection and we're checking the areas around there to see if the symbol has shifted slightly one way or another. This means that the code will take much longer to run, as we are for each possible start selection we are decoding every single one of them. Therefore we're doing this around 20 times for each. So this loop here should take about 20 times longer than a single pass in the other time. However, we expect to see far greater results as we're finding the exact symbol start. Again, we are using our phase error to adjust the frequency samples here before it is put back into a bit stream. Okay, that's all the same. And let's run that. Run and time it.
2 seconds, we just ran the wrong file.
Okay, we ran the wrong file.
Bear with us.
Okay, double pass. Run and time. Okay, and here we are on the receive side of the double pass. As you can see, very little error here, and you can see Einstein there in all his glory.
This time it only gives us 7% error.
As you can see,
But
it takes
It took a lot
takes
longer to run.
significantly longer to run.
Unsurprisingly, twice the length.
Okay, and you can see here we've got an error rate of 7.